Hello, everyone, and welcome back to Conversations with Tyler. Today I am speaking with Carl Zimmer. Carl, as far as I know, is the only person who has both a tapeworm and an asteroid named after him. The proximate reason for this episode is Carl's excellent new book. It's called Airborne, The Hidden History of the Life We Breathe. Carl is also a long-standing columnist for the New York Times. He teaches writing at Yale, and he has numerous other science books on biology, evolution, heredity, and other topics. Carl, welcome.
Thanks so much for having me.
I'm interested in issues surrounding the progress of science. And if we think of the notion of disease being transmitted through the air, it seems that comes to our attention really quite late in time. Late 19th century, it's not truly accepted until later in the 20th century. The idea doesn't seem that crazy. Why did it take so long?
It's a great question and one that I was thinking about a lot while working on this book. And I think maybe part of the issue is that when we look back at history, especially the history of science, we tend to rewrite it. We tend to pretend that things were simpler than they really were. And we ignore all the debates and the way that ideas pop up and flourish for a while and then disappear and then come back again. And I think that the idea that something alive could come through the air and make you sick or kill you was, in a way, in the words of one journalist in France in the 1860s, just too fantastic to imagine. And so it really strained the imagination, even if today we're starting to get used to it. It's a frightening idea because it makes us feel particularly helpless, because, we can wash our hands all day long and keep ourselves safe that way, but you have to breathe. And so I think that there were a lot of reasons, many different reasons for the scientific community to look away and to say, no, this isn't happening or it isn't important.
But birds fly through the air, bats fly through the air, and we've known about little tiny things since the invention of the microscope, which is very late 16th century? So people can't just put the two together. They don't have to have known for sure, but it seems it's just not much even of a candidate hypothesis. Was it really such a big blind spot?
It really was. And, again, things that seem clear to us now were not clear even to, the very brightest minds centuries ago. Now, part of the reason I think is that there was, for thousands of years, an idea that the air itself could actually make you sick. In fact, for quite a long time, the standard view was that if somehow the air became corrupted, it could cause diseases, yellow fever, all sorts of other diseases, and sometimes that would be called miasmas. Miasma is an ancient Greek word. Hippocrates talked about miasmas and really felt that explained why you could suddenly get a lot of people sick all at once, all sorts of different people in a particular place because the air had gone bad. And then in the 1600s, 1700s, there's this group of people who say, we think that there's this invisible world of microorganisms, fungi, bacteria, and so on, as they would be later known, that spread disease, not just in us, but in plants and so on. And experts at the time said, this is ridiculous. You don't have the evidence to prove this, and so on. And so once the germ theory of disease really took hold in the late 1800s, a lot of it was a fight between people who were saying, for example, cholera was being caused by miasmas, by bad air, leading doctors of the time in the mid-1800s. And the people who were fighting for the germ theory of disease, they would say, no, these are being caused by microorganisms, and in the case of cholera, it's in the water. It's not in the air. And so there was this gradual kind of revelation, cholera caused by this particular bacteria, Vibrio cholera, in the water, yellow fever, not caused by miasma, but caused by mosquitoes carrying a virus, and on and on and on and on. And so eventually some leading public health experts in the early 1900s just said, all this concern about the air, this is just this obsolete miasma concept, and we just rest easy, just put it aside. It doesn't matter. I mean, literally, some people put that in print, and so that was really a very strong consensus. And so even in the 1930s, when some crucial experiments started being done, people were still very much primed to ignore it.
When are airborne allergies first understood?
Well, it goes back to a British doctor in the 1860s and 70s, Blackley, who actually thought that he was sneezing because because of of pollen in being released by grass. He would walk by these hay fields and he would have this terrible hay fever, and he'd say, "I think there's something in the air." And so he would rub the pollen, put it in his nose, and start sneezing, and he would say, "Well, okay, this is not a good sign." And then he started to wonder in an incredibly visionary way, like, well, okay, these plants all around me, they're releasing pollen into the air. Where does it go? And no one could say, because pollen grains, they're too small for you to really follow them by the naked eye. So he would do these amazing things, like he built himself a kite, and he put a little probe on the kite where pollen grains could stick to, and it went up. He flew this kite over 1,000 feet in the air, and he would bring it down, and sometimes he would find pollen grains on it. And it was really astonishing. I mean, he would fly it over the ocean when the wind was coming from the sea, and he would still get pollen grains. And he would say, like, I think that the winds are carrying these living things for hundreds of miles, thousands of feet in the air. And this was a kind of an idea that very few people at the time really were appreciating. Now, people thought, "Oh, this is silly." When he published his results, a lot of people dismissed it. They were sure that hay fever was an infectious disease caused by bacteria, or some people thought, well, it's a neurosis. And it really wasn't until the early 1900s that, after Blackley had died, that it became clear that no, actually, what's happening is that when you're exposed to certain things, like pollen grains that you inhale, in some cases, it's your own immune system that is mounting an attack on them and making you feel miserable, makes your nose run and makes you cough and gives you all the symptoms of an allergy. And so, Blackley himself never really got to see that he was actually right. And but it wasn't that he was getting sick. It was in a way that his own body was mounting this incorrect defense called an allergy.
But shouldn't that be one of the easiest hypotheses to establish? So the seasons change, right? The pollen mostly goes away, your allergy goes away, or you clear the field of pollen, or you move house, and your allergy changes. Shouldn't people have figured that out in 800 AD or whenever, just right away, and everyone else accepts it because it's common sense? Are we that stupid?
I think great ideas can just sit around for a long time waiting to be discovered. And I don't think that's unique to airborne disease. I think that's really true across the board for a lot of different sciences. I mean, certainly, a lot of historians of science have said, Charles Darwin, brilliant guy, but really, the evidence was there for a long time. Someone else should have figured this out first. But
at least the church is an opponent, right? So you might be persecuted. It's easier for me to understand that mistake. But even that one broke through.
It did break through, yes. And I think part of the issue is sort of the structure of science. So when I'm telling you about this story about this British doctor who's flying kites trying to catch pollen grains, it's just one guy. It's just one person who's really miserable with hay fever, who's trying to understand it for himself. And, science really works by numbers. Like you actually like have to study lots and lots and lots of people. And then, if you're going to try to tie people's symptoms to the environment in some way, well, you're going to have to track them over months, years, and so on, because the environment is changing all the time. Everybody who suffers from hay fever will tell you, like, well, I don't know. For some reason, this spring, it's not so bad. I don't know why. That doesn't mean they don't have hay fever. It just means that the environment that's causing the hay fever is changing a lot. So there are some basic challenges to really appreciating how what we're breathing in is affecting us.
Why was it so hard, at least at first, for the WHO and CDC to talk about and admit the airborne transmission of COVID-19? That to me also seems inexplicable.
That was, in a way, one of the entry points for me into writing this book, because, during the pandemic and, the outset in 2020, a lot of reporters like myself, we were scrambling to write about this entirely new disease. And we were talking with scientists who themselves were scrambling to make sense of this, new virus on the scene. And so there were lots of questions, and it seemed really peculiar that there was this big conflict that broke out about how COVID spread, and that it took quite a while for the World Health Organization and the CDC to really just say out loud, COVID is airborne. Now, that is laid out in documents online. That is generally accepted that airborne transmission is a really important way that COVID spreads, and it does a really good job that way. And so that led me down this path to try to understand why it is that there was this inertia. And I think it goes way, way back. And it goes back to these battles I was talking about over the germ theory of disease, and the way that, airborne transmission by the early 1900s was really being seen as something that was just not significant, not something to worry about. And so even when strong evidence was being put forward by people who we've long forgotten about, people like William Firth Wells and his wife Mildred Wells, other people were looking at the results and being like, I don't know, I'm not going to accept that. There was a consensus, and then that consensus became established as part of public health policy. And it's also true that if you acknowledge that a disease is airborne and you really want to deal with it seriously, it's going to take a lot to really address it. I mean, if something is just spreading by dry droplets on surface and so on, you can tell people just wash your hands, disinfect surfaces, and you'll be fine. But it's quite something else when indoor air is starting to become rife with these pathogens that we're exhaling into it.
But the common cold is airborne, measles, many, many other things. The common cold is a kind of coronavirus, right? So even taking their bureaucratic nature into account, I still find it utterly baffling that they would have resisted that rather than issuing open statements that would have given them an out in either direction. How do you model them bureaucratically?
I think that public health is just a really challenging line of work, because you want to reduce death and disease by coming up with measures that are going to apply across the board to the public. And that depends on what you understand about the disease you are trying to deal with. And then when you're dealing with diseases where we don't know that much about it yet, you're in a very tricky situation. Do you go extremely cautious, and say this could spread in any different way, and we have to completely silo ourselves off? Or do you say like, well, we don't have clear evidence that it's airborne, so you don't have to worry about that. Where do you draw the line? Public health policy is a hugely difficult and contentious area. It's been, since the start of public health. Now, along with that, there's the scientific question of whether these things are airborne or not. And you mentioned measles, for example. It really wasn't until the 1970s that people really agreed that measles are airborne, even though it's incredibly airborne. It's the most contagious disease that we know of. COVID might be, in the same ballpark now, but it took a long time for people to amass the evidence to really persuade the community.
What's the rate of return to further investment in ultraviolet lamps now?
It could be really quite large. I mean, I haven't seen, economic calculations of that, but um, as I write in Airborne in the book, the idea that you could safeguard the air with ultraviolet light is not new. And in fact, William and Mildred Wells were demonstrating it in the 1930s. They actually put ultraviolet lamps up in a couple schools in the Philadelphia area and protected the children there from measles outbreaks. They did all sorts of other experiments to at least show that there was a potential promise there. Ultraviolet lamps could potentially really help in certain places to make it possible to just go about our business and relax, because the air around us is being disinfected. And there still needs to be more research to figure out how do you use these lights to safely protect large volumes of air. How do you want to make sure that the ultraviolet radiation isn't itself like creating any harmful compounds in the air that you might breathe, and that might be a problem. But these are all things that could be addressed. And so ultraviolet light could definitely be a part of a real serious approach to keeping indoor air safe.
But maybe my worry as an economist is that it ends up being too much like patchwork. So you can take any arbitrarily small area and maybe make it safer. I don't pretend to know the science, but say you could. But unless you have ultraviolet lamps more or less everywhere, you're just redistributing, where people will pick up the disease or the other problem. Isn't there a property rights issue that makes ultraviolet lamps unlikely to succeed?
Property rights in what sense?
Well, there's so many different property owners who would have to do it. You would need a very clear majority of them. Otherwise, you're just sort of pushing the problem around, like toothpaste in a tube.
Well, it's certainly not the case that, ultraviolet light would be like the sole trick to protect us from airborne diseases, from new pandemics that travel through the air. But building engineers who have looked into this and have developed ideas have been arguing that you could put out standards for how clean your indoor air should be, how free of disease, and then you could meet those standards in a number of different ways. So one way would be ventilation, fresh air. If there's plenty of life outdoors, but that life is much more dilute than what you get in poorly ventilated indoor places. So there are lots of ways to bring fresh air into indoor spaces. And there are air purification systems, there are filters and so on. There are lots of different things that can be brought to the table. And this is an area of new research too. The U.S. government has a $150 million project underway to develop cutting edge new sensors that would basically like be able to tell you, we're detecting flu virus, in this building in real time. Those kinds of technologies could then be yet another way to make sure that the air we breathe is safe.
How should we reform ventilation in schools?
Well, there are actually schools that are already doing this. It's a very patchwork thing, but if you look at places like Denver and Boston, they are using combinations of these technologies. So they're improving the ventilation. They're putting in filters. They're sometimes putting air purifiers in individual classrooms. And also, most importantly, they're finding ways to see how healthy the air is. The simplest way to do that actually is just to measure the level of carbon dioxide in the air. This is something that actually like people figured out in the mid 1800s, as I write about in the book, because, if you are sitting there and you're talking to me and you're exhaling, you are, filling the room you're in with carbon dioxide. And if you don't have a window open, it's just going to keep building up gradually. So the level.
Amazing they figured that out before they figured out airborne disease, right? Because carbon dioxide is truly invisible.
Exactly. Yeah, it is an amazing history, and you really scratch your head. And I think one of the most amazing things about that realization is that it was made by a German hygiene scientist named Max von Pettenkofer, and von Pettenkofer himself was actually a huge champion of the idea of miasmas. And he believed that cholera and typhoid and all these other diseases were caused by gases that came out of the ground. He had no tolerance for this idea that you were actually ingesting bacteria. He just thought that was ridiculous. He even swallowed a whole tube of cholera once to prove that cholera was not caused by waterborne bacteria. He was that serious. He didn't feel very well, but he survived, and he decided that proved his case. So great discovery about carbon dioxide. It was such a great discovery that when people talk about sort of the safe level of carbon dioxide in a room, sometimes people put it around 1,000 parts per million. They call it the Pettenkofer number. So he lives on, and yet he was also incredibly wrong about a fundamental fact about airborne infection. Science just doesn't follow a neat path the way we'd like. And in a way, that's one of the things that makes it so interesting to write about.
I often hear that when I'm flying on a plane, the air is quite good and well ventilated. Not boarding, not deboarding, but during the flight. Is that true?
Yeah, I've talked to a few physicists and air quality experts, and yeah, they generally agree that most planes have really good ventilation systems and filtration systems on board. So certainly, if there's somebody with an airborne disease like COVID on your flight, basic physics is going to dictate that, when you're flying and that system is actually running, your risk is going to be lower because they're going to pull pathogens out of the air. On the other hand, when you're boarding and those systems aren't on yet. And so, and lots of people are breathing in a small space, and they don't even have to cough. I mean, people can just exhale, talk, and they might be releasing tiny droplets that float around and can float through the whole cabin. So that's a issue. And then also, if you were to take one of these carbon dioxide meters on a plane, I own one. If you take one on a plane, and you'll notice when you land that the carbon dioxide level will go way back up again because they turn the filter system off, and you're taxiing around on the tarmac and waiting to get out. So certainly, it's something to bear in mind when you're taking a plane. If you're going to decide whether to wear a mask or not, and that doesn't mean that your risk is zero when you're way up in the air and the system is running full strength.
Did anti-COVID masking work?
It worked in the sense that there are a number of studies that show that in different situations when masking policies were put in place along with other measures, you would see a reduction in risk.
But are they randomized controlled trials? I mean, do we really know?
Well, there's been a debate about randomized controlled trials for something like masks, and so certainly there are some experts who say like you can only judge this based on randomized controlled trials. But there are other experts who say, well, that's a bit like saying we need a randomized controlled trial to show that hard hats work. That the physics shows you how it works. Now, do people need to use these things carefully? Yeah, definitely. But you can actually show you can study the way that these masks trap particles and so on to show that you're just going to breathe less, virus-laden air. And also, randomized controlled trials themselves, they can be very effective in many different settings, but they're not perfect. And so, if you run a clinical trial with poor study design, or if you analyze it incorrectly, it's not going to be as good as if you were to be taking more careful measures. So there is certainly I would say yes, there's certainly a debate that's going on in the community, but certainly in a number of reviews that have been coming out recently, the consensus is that masks do help.
I would think the strongest argument for masks was simply that a lot of people hated them, and so they would stay home instead, and we know that would work. But when people are making analogies to things like hard hats, where it's very, very obvious physically what's happening, that's a sign the argument is quite weak. And if I go to a social gathering for 2 hours, either with a mask or without a mask, and I don't mean the highest quality medical masks, we know they work, I think it's highly uncertain whether masks work. And I've read a good half dozen of those papers. I didn't think they were really very good. I came away agnostic, not convinced masks don't work, but it seemed to me the public health community was far too optimistic about masks and were not really following their own standards of evidence. Why is that wrong?
Well, there are many different aspects to just something as seemingly simple as masking. So part of the question is, what kind of masks are we talking about? The Centers for Disease Control, when it decided, maybe COVID is spreading through the air, and we need to think really fast of ways to stop it, and we have this shortage of surgical masks and N95 respirators, they said, well, just put on a cloth mask. Maybe that will reduce the risk somewhat. And that was a public health measure based on, some small studies from a few years before. But again, there are cloth masks, there are surgical masks, there are N95 masks, there are these sort of masks that are called duckbill masks. And so, when you're asking, does masking work? One of the questions is, well, what kind of masks are we talking about? And then we're saying, well, how are people using those masks? When people say they're using the mask, do you see them with their nose hanging out of it? That's not going to work in the same way that, if someone if you say, motorcycle helmets will help reduce deaths on the road, and if people are if sometimes you see someone with a helmet on and it's unstrapped, and you're like, well, that's not going to work. So there are a lot of these questions that go into it. And so, yeah, you will certainly see some studies that may not inspire you. But, I've looked at a lot of these studies and talked to a lot of experts, and I would say, just judging from where we are now, that's the consensus that I described before.
What's your best theory about the anthrax mailings?
Well, I can only go on, all of the investigations that went into this at the time. Just to refresh people's memories, in the wake of 9/11, and when these planes crashed into the World Trade Center and into the Pentagon, there was a real fear about an airborne disease attack, because biological weapons, which are basically weaponized airborne diseases, they had been developed in the United States and elsewhere for decades. And so there were these worries that maybe, Iraq or terrorist organizations had gotten hold of some of these weapons and were going to use them. And the first hint that this might have happened was that the envelopes started showing up at news offices and elsewhere with powdered anthrax, and people would open it up and it would go into the air, and they might inhale it, and in a number of cases, people died. And so the first idea was that this was this must be Al Qaeda. There must be a terrorist attack. This is what we were terrified of. But all those fears and all that terror actually kind of, I think, sort of distracted people. And, it took quite a while for the FBI and various scientists to get a better handle on it. And when they looked at the actual anthrax itself, they said, well, this looks actually like this is not something that was made in some Soviet lab. This looks like it was just here in the good old US of A, specifically at Fort Detrick, which was kind of the headquarters of this aerobiological germ warfare research since World War II. So, there was a person who was identified by the FBI who, and was going to be arrested, and he committed suicide before he could be arrested. So, I don't, I think that it's plausible that, he was the one. I certainly haven't seen compelling evidence of alternate ideas, but
But there's been no evidence actually linking him to it. You would think, well, once he's dead, it would be easy to find all the ties, the connections, things in his home, notes he made, something. But as far as I know, there was nothing.
Yes, and there have been right, and there have been people who have questioned, zeroing in on him, and people who have sort of come to his defense as someone who wouldn't do something like this. But until there's more evidence, it's really hard to make a theory that would be a responsible one to consider.
As you note in your book, the field of what's called aerobiology, there's been a lot of military and national security, almost a kind of domination of the field, a lot of funding, but also a lot of influence. Annette, do you think that has helped or hurt the field relative to the counterfactual of that not being there?
I argue in the book that the way that aerobiology got turned into biological warfare was quite a tragedy, because this was a science that at the time was just getting off the ground. And in fact, the very name aerobiology had been coined in 1937 by a researcher named Fred Meyer, who was really kind of emerging. He was really going to lead aerobiology into the modern age and going to turn it into what might have been a really remarkable new science. He died in a plane crash. That's what happens when you're looking for life in the air, unfortunately. And shortly afterwards, in World War II, the U.S. military basically started classifying lots of information about how diseases spread through the air, and lots of people came to what was then Camp Detrick to do research that could have been really helpful to understanding airborne disease if it hadn't been classified, but it was classified. Most of it stayed classified for a very long time, and it was just sort of almost like a brain drain. And so William Firth Wells, who I mentioned before, who really pioneered the idea that you can get sick from the air around you inside of buildings and so on. He had no idea that a lot of his basic ideas and technology had been used by the Army in World War II to develop this biological war machine. And he was appalled after the war. He said the way he described its effect on science, it was the suicide of bacteriology. In other words, he just thought this was a terrible thing for scientists to do, to instead of trying to look in the air and figure out how to protect lives, to develop better and better weapons for killing people, for causing mass starvation, and so on. And this was true not just in the United States, but in other countries, especially the Soviet Union, where there was this focus on trying to use aerobiology as a new kind of theater of war. And it even affects our public health, I would argue. Then instead of looking at public health as an opportunity to sort of reform the conditions in which we are in order to promote health and well-being, to some extent, public health, especially in the United States, became sort of, a fight against an enemy attack. And so you had people, the same people who were building a lot of our modern public health system were consulting with the Army on biological warfare.
Some of my friends worry about microplastics in the air. Should they worry?
I think we need to be studying this. Absolutely. There's no question. I mean, in my book, I'm really focused on living things in the air. We have put lots of other things into the air. And so microplastics are a new addition to air pollution. But, even good old, particulate matter from cars and power plants and so on, kills several million people around the world every year. It's a major attack on human health. So yes, microplastics, I think, certainly bear more research, not just in the air, but in our water, everywhere.
I have some questions about your other books. How much do you think there's life on icy moons, typically in oceans?
Yeah. So in my book, Life's Edge, I was writing about kind of, how far we can push our concepts of life and can we think about life elsewhere? And I certainly think that the icy moons of the outer solar system are the most interesting place to look for life. Mars, that's great. That's fine. I wish them well as they're digging through the dust and the dirt. But imagine drilling down through the ice and sending a probe into a huge ocean. What is that world like? It might have life in it, or at the very least, it might have some really interesting chemistry. Maybe these are places where life has yet to form. So I can't say whether there's life there or not, but there's certainly good reason to think that there might be life there. And if there isn't, that might be a place to kind of get some clues about how life begins on places like our own planet.
What's your point estimate for there being life on the icy moons in our solar system?
I have not done that math.
But there's some bet I could offer you where you would take it, right? Just intuitively.
If
I offer you 100-1 odds, you'll take the bet, right?
Yeah, 1,000-1 odds. Yeah, I think it's. Let me put it this way. I think on a planet by planet, moon by moon basis, it's very unlikely that there's life out there. But there's so many planets and moons in even our galaxy that I'm sure that there is life of some form elsewhere. Whether it's right next door in our solar system, I think it's highly unlikely, but I think it's likely enough that I would love for us to go check it out. And even Venus. There are actually other people who say, well, forget those icy moons, forget Mars. What about Venus? And this actually ties into Airborne, my book, because you might think Venus, that's crazy. I mean, it's so hot on the surface of Venus, you can melt lead in that air. But the fact is that when you get pretty high up in the atmosphere there are clouds up there where things aren't that bad. And, we have clouds here on Earth that have lots of microbes in them. They get into the clouds, they hang out there, then they fall back out and more come in. So there could be this sort of aerial life on Venus. Maybe life started on the surface of Venus and then rose up into the air, and now it's staying up there. There are a
So
lot of people.
we're at n equals 2. The one ocean we know has life. The one set of clouds we know has life. And you won't take 100 to 1 bet that there's life somewhere else in the solar system. I would think you should take a 10 to 1 bet on that one.
Well, no one's offered me the money yet, so I haven't really had to put my money where my mouth is yet. But yeah, it's something to think about.
Is Lee Cronin right or insane?
So Lee Cronin is a chemist in Scotland, University of Glasgow, and he has this idea that you can explain life with a theory that he and others call assembly theory, which is about basically like how many steps does it take for something to get produced, and the things in our bodies, the molecules that make us up. Some of them are very small and simple, but some of them are exquisitely big and complex. And Lee and others argue that that life is what is able to assemble things beyond a certain threshold. And so this might be a way to actually identify life on a planet, even if you don't know what life is made of. I mean, we can't assume that life is just made of DNA. That's an unreasonable assumption. Life might, life on Earth already blows our minds in many ways, at least mine. But life on other worlds, maybe that bet is right, and there's life on Enceladus or some other icy moon. It might be really, really, really strange, but maybe we can recognize it by this assembly index. Not only could this assembly theory be a way to recognize life, but it might be actually a way, Lee Cronin thinks, to make life. And in other words, it guides you in basically creating a set of chemical reactions where you're creating these. Right now, he's got these robots that are basically making droplets with different chemicals in them in these vast number of combinations. And he's wondering if they will eventually start to sort of take on some of the hallmarks of life. So in other words, yes, he is trying to make life. He's actively trying to make life right now. And a lot of people think he's kind of crazy. A lot of people think he's quite brilliant. Some people think he's both.
I like him. I don't know if he's right. He's a lot of fun to talk to.
Absolutely. Yeah. And he has, it's been really interesting watching assembly theory sort of come to the fore recently. And some scientists really take badly to it in a very hostile way. But as is often the case, it feels like sometimes people are just talking past each other, and they're not really speaking the same language. So I think because assembly theory is new and it's very interdisciplinary, I think it's going to take a while for the scientific community to really engage with it and decide whether it holds up or not. I look at this as, I think, as I argue in Life's Edge, life is a property of matter. And scientists are trying to explain it, and some of them are trying to explain it with a theory. Superconductivity is a property of matter. And there were a bunch of theories that were put forward about it, including by Einstein, and they were wrong. And it wasn't until eventually some people came up with the right theory that really clicked in and had a powerful explanatory power. So we're not there yet with life. And so maybe Lee Cronin is going to be like Einstein and he's wrong, or maybe he will be one of the people who is right.
Over time, how much will DNA information enter our daily lives? So to give a strange example, imagine that for a college application, you have to upload some of your DNA. Now, to unimaginative people, that will sound impossible. But if you think about the equilibrium rolling itself out slowly, well, at first, students disclose their DNA, right? And over time, the DNA becomes used for job hiring, for marriage, for in many other ways. Uh, is this our future equilibrium, that genetic information will play this very large role, given how many qualities seem to be, at least 40 to 60% inheritable, maybe more?
Well, there's the term that a scientist in this field would use would be heritable, not inheritable. And heritability is a slippery thing to think about. And I write a lot about that in my book. She Has Her Mother's Laugh, which is about heredity in general. And heritability really is just saying, like, okay, in a certain situation, if I look at different people or different animals or different plants, how much of their variation can I connect with variation in their genome? And that's it. That can you then use that variability to then make predictions about what's going to happen in the future? That is a totally different question, in a
But it's
many
not
actual.
totally different. I mean, your whole family's super smart, right? If I knew nothing about you and I knew about the rest of your family, I'd be more inclined to let you in TL, and that would have been a good decision. Again, only on average, but just basic statistics implies that.
Well, you're very kind, but I'm. I mean, what do you mean by intelligent? Like I'm. I am I'd like to think I'm pretty good with words and that I can understand scientific concepts. I remember in college getting to a certain point with calculus and being like, I'm done. And then watching other people like sail on.
But look, you're clearly very smart. The New York Times recognized this. We all know statistics is valid. There aren't any certainties. It sounds like you're running away from the science. Just endorse the fact you came from a very smart family, and that means it's quite a bit more likely that you'll be very smart too. And eventually the world will start using that information, would be the auxiliary hypothesis. But I'm asking you, how much will it?
Well, the question, that we started with was about, actually like uploading DNA. And so then the question becomes like, how much of that information about the future can you get out of DNA? And, I think that, you just have to be incredibly, cautious about jumping to conclusions about it, because there are, the genome is a wild and woolly place in there, and the genome exists in environments. And even if you see sort of broad correlations on a population level, I would not, as a college admission person, I would certainly not feel confident like just scanning someone's DNA for information in that regard.
No, that wouldn't be all you would do, right? They do plenty of other things now. But over time, say for job hiring, we'll have the AI evaluate your interview, the AI evaluate your DNA. It will be highly imperfect, but at some point, institutions will start doing it, if not in this country, somewhere else. China, Singapore, UAE, wherever, they're not going to be so shy, right?
Um, I can certainly imagine people wanting to do that sort of stuff, regardless of the strength of the approach. And certainly, we have seen, even in the early 1900s, we saw people more than willing to use ideas about inherited levels of intelligence to, for example, decide, what people, which people should be institutionalized, who should be allowed into the United States or not. So, for example, Jews were considered largely to be, developmentally disabled at one point. So, especially, the Jews from Eastern Europe. So, like, we have seen that people are certainly more than eager to jump from the kind of the basic findings of DNA to all sorts of conclusions, which often serve their own interests. And I think we should be on guard that we not do that again.
Will embryo selection ever become, completely socially accepted?
That is
Because there are people doing it now, right? It's not yet a thing, but it's growing.
well, certainly, I mean, with IVF, people are going to want to select the embryos that have the most likely chance of surviving. So you're going to take a look for any sort of clear abnormalities, and it certainly is possible to let's say that you have a dominant genetic disorder like Huntington's disease. The technology is there that you could say, like, okay, we created these fertilized embryos. Let's not use the ones that are carrying this marker. But you can even go before that. Potentially, you could say, like, okay, we're gonna, like, even before fertilization, say, like, okay, we're gonna just take out the sperm or the eggs that have a marker that for one of these strongly inherited diseases like Huntington's disease. Will people then move on to that future like that? I can't predict whether they will or not, and whether they should or not, I think, is a separate issue. But again, I think one of the dangers is that people will convince themselves that the information we have about DNA is going to ensure things about their kids that they can't be sure about. And then you're going to have this sort of lifetime of watching your kid not live up to your genetically encoded expectations. I mean, that's one of many dangers I see in going down this road.
Why do you think the Flynn effect seems to be so especially strong for the Ravens part of IQ tests? This has puzzled me for a long time. Do you have a hypothesis?
I mean, I certainly haven't done any, my own original research on it. I'm a journalist, not a scientist, but
you've read plenty, right? I mean, you have
sure.
a sense of the field.
Yeah, no, absolutely, I've read about it in part because it's just this fascinating thing that there has been this increase in IQ scores, and it's certainly not a result of some sort of genetic process. You cannot explain a rise in IQ scores in so many different countries because somehow people are being born with different kinds of DNA in some sort of like evolutionary process. That is not happening. So what is happening? And I think that there probably are several different explanations for it. And I think, I don't know. I mean, one of them might be that, kids grow up in an environment that, where just everyday life is more about the kinds of thinking that you encounter on an IQ test. Like what people are using digital devices, for example, and just like there could be just a way that the kind of life we're leading just leads to people doing better on IQ tests. Now, certainly some people do better than others. And, is there an influence of DNA on that? Yes. I think the evidence is there that there is. It's not necessarily a huge account, but in any case, you can have these different things happening all at once, is something interesting. It's frustrating that, it's really hard to actually like take these different hypotheses about the Flynn effect. I mean, maybe it's something about our health, but how do you really rigorously test those things? I haven't seen a lot of rigorous tests of the different hypotheses. I've just seen people say, like, well, this could explain it, which is fine, but not totally satisfying.
If we take, the entirety of science, you've written on many topics in a very useful way, science policy. Where do you think your views are furthest from the mainstream or the orthodoxy? Where do you have like the weirdest take relative to the other people you know and respect?
Oh, wow.
Like, I think we should just do plenty of human challenge trials. That would be an example of something you might say. But what would the answer be for you?
You mean human challenge trials for like influenza and things like that?
Whatever we need to, we should have for COVID, right? It would have sped up the vaccine, saved thousands or maybe more lives.
Yeah.
Rather than wait for people to be infected, you infect them deliberately and call for volunteers, right? You can pay them if you need to. So that would be a view I have that's somewhat outside the mainstream, though less outside than it used to be. What would 2 or 3 of your non-mainstream views be?
Well, wow. It's in. The thing is that when I am writing about, the science itself, in terms of like the scientific findings that are just sort of coming out every day, and I tell people about them, they'll say like, "What? That is crazy," and I'll just be like, "Look, I'm just telling you about what scientists are discovering about our world." And so, if I describe what whale scientists are discovering about how whales communicate, I'm not going wildly beyond what they're finding and their theories, but to most people that's crazy that that whales can hear each other across oceans and can change their songs.
But that's mainstream now, right? You're just
Yeah.
endorsing the mainstream, and I would agree with that.
Well,
Like, I think whales might be smarter than humans. That's a non-mainstream view I have. Like, what are your non-mainstream views?
I guess I don't really. It's interesting that I'm sort of drawing a blank on that, simply because like I am just so dazzled by so much that I learn about in terms of the scientific world. So, what is the scientific mainstream is just can be quite mind blowing to everybody else. If I just say offhand, like, oh yeah, there are billions of microbes in that cloud you see in the sky, people say like, you're crazy. I'm like, I'm not crazy. So I am a sort of scientifically mainstream sort of person, I guess, and to everybody else I seem a little crazy.
Younger in life, what is it you learned about New Jersey politics? Noting your father was a former New Jersey congressman, Dick Zimmer.
New Jersey politics is it got a rich, long history of corruption and just rough and tumble kind of activity. I was, very proud just to see my dad, stay above that fray. I live in Connecticut now, and Connecticut's got its share of corruption too. But still, New Jersey was really quite a place to see all sorts of scandals in action.
So you learned that a non-corrupt New Jersey politics was possible. That's a non-mainstream view, right?
Well, it certainly was my experience growing up with my dad. Yeah.
And his district was what? Near Monmouth County or Delaware River? Where did you grow up exactly?
So when I was 10, we moved to pretty close to the Delaware River in Hunterdon County in New Jersey. And so that was when my father was elected to Congress, that was his district.
Before my last question, just to endorse Carl's book again, Airborne, The Hidden History of the Life We Breathe. And indeed, I'm a fan of all of Carl's books. I think I've read all of them or very close to all of them. But very last question, what will you do next?
What will I do next? I'm working on a podcast. I can't really talk about it at length right now. There'll be more details later. So I'm kind of entering your world a little bit, and it's fun and frightening. And then it'll just be a question of thinking about what the next book is. And I generally just let those ideas come to me, because it's got to be something that's going to really be something I can live with for years. And so I don't choose the next book lightly. So it hasn't come yet.
Carl Zimmer, thank you very much.
Thank you.